Well, welcome everybody. Thank you for coming out. It's kind of freezing out there, so we're happy to have you here with us today. Some of you aren't too familiar, so I just let you know that this is a monthly programming series, the Sky Watchers, and we go from different branches. So next month is going to be in Thompson. That will be January 10th, and it's going to be about Saturn. We'll take an in-depth look at the ringed planets. So that'll be next month. This month, there's some materials on the table behind you there, some handouts, and you can check out anything on that table. We also have telescopes at all the Geauga County branches that you can check out, which I don't have ours in here today. If you're interested in that, you go to our website. There's a little quiz you take. It's just a 5-minute video and then a short quiz. It's not too challenging. And then once you've taken that, you're qualified to check out a telescope, and you can check one out at any of our Geauga County branches. So, all right, with this.
You don't have to wait. Leave here your neighborhood expert on the upcoming special holiday in December that's linked to what's going on in nature. You have no idea which one I'm talking about, right? Which one am I talking about? Right, it's the winter solstice. All right, no surprises. We're going to talk about the winter solstice. I'm going to call it Solstice Science. Why we talk about the winter solstice now and not in November or January? Because it is a very special date. Anybody really feeling like showing off their astronomical knowledge? The date for the winter solstice?
21st.
December the 21st. All right, I can't pull anything past you guys. All right, nice. So you guys have the absolute basics. So we will we'll get on to the good stuff. We'll make this as complicated as you guys want to get, because like any I like to start these with a little preview of what's going on in the actual nighttime sky. So, unrelated to the solstice, something really cool to look for in the winter sky this month is that there's 3 planets right in the evening sky, right after sunset. So I'm trying to show this in these cool pictures. The sunset is at the lower right corner, and then there are 3 planets in a nice straight line right above them. So if we ever get a break in the clouds, I kind of hope we can get a chance to glimpse that tonight, but we'll see what the weather gives us. The good news is this isn't like an eclipse that only lasts a few minutes or hours. This lasts all month that these 3 planets are going to be up there. And so we think this is happening because we shift from living on planet Earth to looking down at a map of the solar system. If you can hover a few billion miles up above the sun's north pole. We're here on the Earth because that's where I live, and I don't know about you, but I've spent my entire life here on planet Earth. And that's where we're stuck observing the solar system from. But as the outer planets, farther away from the sun than we are, loop around, every once in a while they line up like this. So this is what we were getting. And yeah, so we're catching up just in the early evening before they're blocked by our own rotation. Oh, good stuff. So my next question is, how often does this happen? Wow. These planets lining up. What's that?
Once every 10 years?
That's a good guess. Actually, if anybody remember December of last year, I know that was so long ago. We're low in the evening sky, right up at sunset. In fact, they even almost lined up with each other. They were really close. Wait, let me go back. So here's about how far apart. You'll be able to hold your fist up in between Jupiter and Saturn this month. But last year, well, here's my fun time-lapse animation. They kept creeping closer and closer together over the course of the month, until amazingly coincidentally, on the night of the solstice, they were really, really close together. Like you could have held a dime up and covered both. Of course, it was very cloudy that night, so we didn't actually get to see the closest, but you know how December is.
Does that mean that one, I don't know which ones, the smaller one is bigger?
Oh, good guess. So in this one, I know they look smaller, so when we draw these...
Relative to each other in that picture?
Yeah.
I don't know.
No worries. So the one that looks bigger is because it's brighter, so it's hard to show that, things look brighter in the sky, so you just make a bigger dot. So the bigger one is actually Jupiter, because it's closer to us and it's larger, so it reflects a whole lot more sunlight at us. Saturn looks fainter.
But my main question was, is it because one's orbit is faster than the other?
Oh yeah, let's go back.
It's closer to us.
There, high five. Absolutely, that's it. So yeah, the general rule in our solar system is the farther you are away from the sun, the longer it takes you to finish your orbit.
Right.
So in here, where it's even hard to see, I didn't even put a dot show Mercury, that's barely like 88 days for it to circle the sun. And then it takes 1 year by the time you get out to the Earth, and then more than a decade by the time you're getting out to the outer planets. So yeah, year by year, the next couple of years, we're going to see this every December. They're going to appear fairly close to one another. Last year was the closest they got. But the good news is we're going to get this cool winter show because they are in the kind of outer lanes, and we're whipping past them on the inside lane every year. So that's something cool to look for anytime we actually get a break in the clouds this month. Oh, good. Okay. But on to the Solstice Science. Ooh. So I didn't really introduce myself, so I'm Chris Mentrek, and I work at Observatory Park, the kind of space-themed park in the Park District. So raise your hand if you've been to Observatory Park. Raise your hand if you've never been to Observatory Park. Okay, we've all been there. Oh, good. Most of us are sure. So if you've been there, you might have noticed there's this cool thing in the pavement. Ooh, right outside the buildings. And at the heart of it, it's got a compass that helpfully shows you where north and south and east and west are. And there's a big line that continues the north-south line. Then there's these other lines going off in other directions. And they're related to something. Not just north and south, and east and west, where the sun more or less rises and set. What's going on in these other lines?
The solstice.
Oh, you guys can totally guess it's connected to the solstices. Nice, so air high five. I can't pull any fast ones past you guys. So what we did was we tried to show, and I think I've got a laser pointer here. I'm going to try and make this work. Oh yeah. Ooh. I guess that's a little hard to see. Never mind, I'll point the old-fashioned way. So yeah, there's one to the northeast, one to the southeast, one to the northwest, and one to the southwest. But not exactly northwest. They're in vaguely that quadrant. And so what we tried to show you is where the sun can rise and set over the course of a year. And so like I said, everything when we study nature has different levels of complexity. I always tell the G-rated version of the story of where the sun rises and sets is the sun rises in the east and sets in the west. Nice, that's the G-rated version for little kids. You folks are old enough for the PG version, which is a little bit more complicated. The sun doesn't always rise exactly in the east. And we've probably all noticed these. If you've been through enough springs and summers and winters and falls, you notice the sun changes its position of sunrise and sunset. So we literally set it in stone to help you remember where it is. So off roughly towards the northeast, on the sunniest day of the year, I should say the day with the most sun-filled hours. And that's the other solstice, not the December solstice, but the
Summer.
You guys are the best, the summer solstice. And that's not June, I gave it right away, it's June 21st. It's not December the 21st, it's June the 21st. About 6 months apart. Nice. Well done. So yeah, so that's our summer sunrise, the farthest north the sun rises. And then every day after the summer solstice, the sun will rise a little bit farther south. Day after day after day after day, until eventually it's rising, in the southeast. And on that same, go ahead.
So, that the summer solstice is rising in the northeast. What degree is that?
Oh, nice, that's on your forms. Oh, I'm gonna give you a hard one. People are gonna think I hired you to ask that, because we are literally going to calculate that later. You guys are accessories to recreational math at this point. I like it. So yeah, in case you want to do something like this at home or set up your own mini Stonehenge or whatnot, we gave you the angles of exact sunrise. So on a radar screen or a compass, north is 0 degrees, and then you go this way. So this will be 90 degrees is east, 180 degrees is south, and it goes around that. Good stuff. And so then on that same summer solstice, the sun will set, not in the west, but way over there in the northwest. So those are our 2 summer solstice rise and set points. One off to the northeast, one off to the northwest. Kind of cool. And then symmetrically, if you extend those lines the other way, and I've marked them in blue, you'll never guess what this rising point here is over here in the southeast. Oh, it's the winter solstice sunrise. You guys are the best. And then the other one is the winter solstice sunset. So if you live on planet Earth, the sun will rise and set way down here in the south in December, and in June it rises way up in the north. It's kind of cool.
Yeah.
So that's what you get looking down at our thing. If you actually stand in the kind of solstice sunrise marker at Observatory Park, you just look down those lines and it'll point you towards the direction, the azimuth, the heading, where the sun will set. This is facing the winter solstice sunset line. And it's at Observatory Park, it's framed by 2 of those big stone pillars. So I'm fond of saying, if you were really into keeping the dates and you lost track of what the date is in some cataclysm, you could always just hang out at Observatory Park until the sun sets behind one of those. Or you could set one of those up for yourself, and that way you never have to reset your calendar again. So that's the winter solstice, and this is our summer solstice, the other line. And I actually got this one at sunset. You can tell this is my photo because it's not a very good photo. But here's the gentleman setting up his telescope, here's the line pointing, and there's the sun setting right behind it back there in the trees. I am not a great photographer, but sometimes nature puts on a good show. So, ooh. So there we are on a very cloudy winter solstice trying to take the same photo. Oh, good stuff. So we're going to chat a bit about how ancient cultures would mark those, and how you might try to do the same. So like I said, if you lived in the same place for a long time, you'd start noticing that the sun goes through that cycle. And days are short and cold in the winter, and they're long and sunny in the summer, at least here in Ohio. And you might incorporate that into your architecture. So like I said, we've made fake phony baloney ancient sites at Observatory Park to show how this kind of thing would happen. And so we put in these big stone pillars that show where the sun sets on these key seasonal dates in between the solstice points. There's one stone there on the right that marks where the sun sets on the first day of spring or fall, on our equinox dates that are halfway in between our solstices. It's kind of handy, and the other ones sort of function as a gate. But like I said, ours are kind of phony baloney fake things, but the artist made them to kind of evoke certain ancient sites. Does this remind anybody of any ancient sites? All right.
Stonehenge.
Sure, yeah, Stonehenge or some of the standing stones of Northern Europe. So here's a snapshot of my favorite set of standing stones, the Colonish standing stones up in Scotland.
Oh.
And so from northern France to Ireland to Scotland to the Scandinavian countries, there are a lot of different of these big stone or megalithic complexes that people would use to mark seasonal changes. And I really like this one because some photographers took a photo every day of the year at noon, and they made sure that the sun was in there. So that's, well, I should say not every day, it was once a month for an entire year. And the sun traces out this cool figure 8 path.
Wow.
But we'll talk about that again in a moment.
Chris, what longitude, what's the longitude and latitude there?
That's a great question. I don't know. It's much farther to the north than we are, so it's in the 50s, latitude-wise. And I bet the longitude's pretty close to 0 because it's the United Kingdom. It's not that wide.
Yeah.
But that's a good question. We'll look that up at the end. Oh, I like it. I got a cool homework assignment. Oh, nice. So sometimes there are coincidence alignments with ancient sites or modern sites, and sometimes it's deliberate. And it can be a little tricky to piece this out. Like there's a coincidental seasonal alignment at Observatory Park. So we set up so that there's a big stone back there that marks where the sun sets on the equinox. There's also a lamppost there, which is just there for convenience sake. But by an amazing coincidence, it casts its shadow right onto the compass on the equinox dates as well. Did we mean that? No, we just happen to put a lamppost exactly west of our compass point, and that'll happen accidentally. So there's always this risk when you find ancient sites that might be related to a certain date, sunrise and sunset. My favorite example of a coincidence is Manhattan Henge. And so the island of Manhattan is laid out so that the streets line up with sunrise and sunset around May 30th and July 12th every year. And so crowds of fools get out and stand in traffic to snap a picture of this, and I guess it's like a big traffic snarl.
Wow.
So, I mean, 1,000 years from now, I like the idea of some future archaeologist saying, what was special about May 30th to the builders of Manhattan? And if you look at a map of Manhattan, no, it's a northeast to southwest sloping island, and a right angle street grid happens to be really convenient. So, okay, those are my favorite coincidences, but what about some ancient sites that are related to the solstice? And so, yeah, Stonehenge gets a lot of press, particularly among people who trace their ancestry back to the British Isles, and the Newgrange sites in Ireland. But I wanted to show some ones in Ohio that have a solstice connection. So I went with my second favorite ancient Ohio site. Ooh, the Serpent Mound. Oh, raise your hand if you've ever been to Serpent Mound. Raise your hand if that adventure is in your future. Oh, good stuff, nice. It's way down in the southwest, so we're here in the northeast Ohio. It's almost in southwest, south central Ohio.
I thought it was in Newark. No?
Oh, we're totally going to be talking about Newark as well.
That's
There's a huge ancient earthworks complex here in Newark, a little bit east of Columbus, which that's my absolute favorite, and it has this amazing connection to the moon cycle. But okay, back to Serpent Mound. So on the right is one of my favorite things about being an Ohioan is that every year the Department of Natural Resources publishes a new set of satellite imagery for the state for free. It's your right to claim this as an Ohioan. Everybody needed a COVID project. So this is if you really want to spend a lot of time poking around on the internet, you can get the cool new satellite photos. So here's a satellite photo of the Serpent Mound area. All right, can anybody find me Serpent Mound? Probably not. It's kind of a trick question because it's made of grass and it blends into the grass. So this is a map photo. So north is up. Here's the road. Here's Raccoon Brush Creek. And the highlands, because this is southern Ohio, the highlands still have trees on them. The lowlands have been turned into farmlands. So you can kind of tell what's high and what's low. But you notice there's this suspicious parking lot over here in the woods, but no buildings around it. So big crowds of people are coming to visit something other than a building. Serpent Mound is right in here on the edge of the cliff above the river. All right, so let's zoom in a little bit. Ooh.
Wow.
So it stands out a little better when the sun is low and it casts a shadow. So I love this satellite photo because it arranges it, so the north is up. The cool photos that they put on like postcards and it's on the State Historical Site website show it like this.
Whoa.
Which makes the snake look that much cooler. So to give you an idea of the scale of it, that's a standard footpath that's about 6 feet wide. And so this thing is about 1/4 of a mile from snout to tail. And it's hard to judge because its snout is actually off the edge of the cliff and the cliff has been eroded. So it may actually have been a little bit longer than it is nowadays. But one of the coolest things about it is that it's aligned with that cycle of sunrise and sunset points. Okay, so here's how you do it. Ooh. Its head points to where the sun is setting on the summer solstice. Right up there. And then what's a little trickier to catch is the 3 big wiggles in the body, number 1, number 2, number 3, are kind of like 3 fingers. And so it looks a little odd in this picture because north isn't up, but if you go back, here's our north one. 1 finger points due east, 1 is towards the northeast, 1 is towards the southeast. So these are those sunrise and sunset points for the summer solstice, the equinoxes, and the winter solstice. And then the head points to the summer solstice sunset. It's kind of amazing. Ooh. So if you dropped Serpent Mound onto the cool pavement at Observatory Park, its head would point towards where the sun sets at the summer solstice, and its 3 body wiggles are for these sunset alignments on the other side. I think that's amazing. It's its own calendar. If you just stand there and wait at the head for the sun to set right behind it at the edge of the cliff, you've got yourself a calendar and you know exactly what the date is. This is so great and so amazing that it got the greatest honor, in my opinion, in American culture. It was immortalized on U-Haul trucks. So they make these like picture postcards, one for each of the states. The Ohio U-Haul trucks have Serpent Mound with its astronomical alignments on them.
Wow.
Oh, yes. You know that game where you punch somebody if you pass a Volkswagen Beetle? If you ever see one of these trucks, you are allowed to punch whoever's next to you in the car and say, look, it's the serpent moon. And so there are dozens and probably hundreds of Native American sites across Ohio, some that are aligned to the seasons. Like there was a neat one in Conneaut that's on maps from the 1800s, but it doesn't exist anymore. So it's a little hard to verify. It looks a lot like a Serpent Mound style. It's just an oval with a slice through it that points very close to where the summer solstice sunset would be. At least that's what it looks like on a map. Nowadays, we can't go out there and verify it because somebody paved over the thing. So there are like 3 or 4 of these sites that are extremely well preserved, and you can still visit them and see some of these alignments. And I'll put in a commercial for this. Just northeast of Cincinnati is Fort Ancient, a truly amazing ancient site. And in healthier times, they've actually offered winter solstice sunrise tours so that you can stand out here in what was kind of the ceremonial center and watch the sunrise through a gap in the wall that was raised around this enclosure on top of a hill. So I don't know, you guys came out for a cold solstice evening program. If you're willing to get up for a cold solstice morning program, it's kind of fun to watch the sun come back on the shortest day of the year from there. And so this seems to have been incorporated into a lot of different ceremonials across North America. Out west, there are these giant medicine wheels, as they're called, that are made of stone and mark different seasonal alignments and where things rise and set. It's kind of great. Ah, nice enough. But what if you wanted to try this yourself? Ah, this is where math comes into it. Ooh. Ah, nice. So I gave you a compass card on your cool handouts. And for our latitudes here in Northeast Ohio, if you want to mark this out in your yard to the nearest degree or so, you've got everywhere you need for our winter, summer solstice, and our 2 equinox dates. But what if you wanted to get a taste for the math and wanted to calculate where the sun rose on another date and put a stone to mark that, like say my birthday, or maybe you're really into Arbor Day and you wanted to mark that date. So I thought just because it's fun and it shows you a little bit about how the sausage is made in astronomy, I thought we'd go through this calculation. And it's kind of fun because it's not in school, so you're not going to be required to reproduce this on the test. But it shows you what's involved in this kind of fun calculation. All right, you guys ready? We'll try it, but we'll try it lickety-split. Go ahead.
You're killing me because I just put, I got bronze recessed points
Oh,
in my drive patio, and one in ivy and one in some flower bed.
oh wow.
That marks what we're talking about.
That's awesome.
So this is killing me though, because if this doesn't align, I'm in deep.
We gotta do a little moving of your stones around.
I might have to leave halfway through this.
That's all right. That should totally work. I think you'll be pretty great. And so yeah, if you're marking it with a stone, we only needed to get to the nearest degree, so we don't need to make the super fancy calculation. Okay, so I picked a random date. I picked National S'mores Day, which is August the 10th. This is kind of fun. Yeah! So we're going to run through this, which is kind of fun. And it's like spectator math because there's no pressure. There's no quiz, no test. You don't have to worry about that. All right, well, we're going to try and calculate. There's 3 steps to the calculation. Technically, this is an algorithm, but don't tell your math teacher I told you we're doing that. Okay, 3 steps. Number 1, we got to figure out the date. Number 2, we got to find the sun's position in the sky. And number 3 is that we've got to find the exact location of sunrise. So 3 main steps. Ready for it? All right, get your minds lubricated. We're ready to go. Okay, so August 10th, we've got to convert that from the date, August 10th, to the day of the year. We've got to convert it into a number. So in this system, January 1st is 1, January 2nd is 2, December 31st is 365. So if we're going to do August 10th, let's see, how many days are in January? 31. 31, good. February has, well this year it has 28. And so on, all the way up to 10 days into August. So if we add those up, oh my goodness, we'll get a date for August. And I'm not going to force you to do all of that. But if we just kind of estimate it, it's about 30 times 1, 2, 3, 4, 5, 6, 7. Yeah, it's going to be a little more than 210.
23 or something.
Wow, nicely done! Oh man, you get a prize. Oh yeah, you
222.
We've got a cool prize for you. Nicely done. You guys flew through that. Just for that, we're gonna gives you an unfair advantage over a calculator.
Oh,
Well, nowadays, everybody's carrying calculators.
I got one.
Yeah, on your pocket computers. Oh, nice. What's the point of living in the future if you don't have, trigonometric functions built into your thing? So phew, step one is over. Our day of the year for August 10th is day 222 out of 365. 222, that's August 10. I'm writing it down so I don't forget. Okay, whew, we're 1/3 done. Next step, like I said, we need to figure out the sun's position. Like I said, as it oscillates from its solstice sunrise to winter solstice sunrise, summer, winter. So here's where we get to the beautiful part. Ooh. Ah, yes, a proper equation. Ah, yes, and I brought my favorite calculator in there, just in case. I know! So there's a formula relating this, and who doesn't love a formula? So we've got that number D we just figured out. We're going to add 10 to it, and then multiply it by this weird correction factor, 360 degrees divided by 365. You can probably guess what that 365 is there for. How many days in the year? And 360 degrees is the number of degrees in a circle. So like we said, if a full year is 365 days, we're calling that 360 degrees. So we're turning how far around a circle you are in, as a fraction of a year. Nice. So that would be D over 365. But there's this weird plus 10 factor here. Oh, what's going on with that? And I'll give you guys a huge hint. What was the date of our winter solstice? December the 21st. What happens 10 days after December the 21st?
First day of the year.
December the 31st. So the calendar cycle resets 10 days after the winter solstice, which is when the sun calendar resets. So yeah, there's just that little factor there to make it work out. It's kind of cool. Ah, yes. And this 23.5 thing, that's how much the Earth is tilted compared to its its orbit around the sun. That's the latitude for the tropics. Oh, and then there's this beautiful 3 little letters right here. What is that for? Cos. Yeah, it's not for cousin, it's for cosine. Oh, quick aside. Oh, we remember the happy days from math class when we learned about cosines. It was, I know, right? It was probably in a terrible, unpleasant course called trigonometry, where they made you look at a bunch of triangles, and you were like, find this part of the side. I said, no, teacher, you find it. I really don't like how we teach trigonometry, because we talk about triangles, triangles, triangles. The real power of the cosine, sine, and the trigonometric functions is that they describe repeating things that happen in cycles. And so if you're going to do anything in astronomy, trigonometric functions are everywhere, because they describe beautiful motions like this oscillation that we're seeing here. So as you go around a circle, cosine kind of keeps track of what's your horizontal component. And it's great. It shows up everywhere.
I'm getting a rash.
Right?
Me too.
Nice. I kind of like it. I just picked a random example. Here's a map of where Jupiter's moons are over the course of a month. In this case, it's December. So you can see Jupiter's here in the middle the whole month, from beginning to end. And then just to track the positions of the moons, you read along each chart.
Looks like a normal helix.
It totally does. And it's really just a combination of a bunch of these turned on their side. It's great. Like I said, their real power is not triangles. It's keeping track of where you are in the course of cyclical things. This is why anybody who likes radio signals or electronics is really a big fan of these trigonometric functions and sines and cosines. But okay, let's say we actually did that. We started with D was 222 plus 10, 3, blah, 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 blah. We end up with the cosine of 229 degrees, which gives us a number. We multiply that by negative 23.5, and we get the sun's position in the sky on August 10th is that. And I'm going to write it down. Whew, that's step 2 out of 3. We're 2/3 of the way done. And those were the hard steps.
I don't understand.
Oh, no problem. Hang on, I'll be right there. Plus, like I said, there's not going to be a quiz on this. The important thing is that it's what we get at the end. Go ahead, Margaret.
Okay, so go slow. How did you get the 229 again?
Oh, sure. So if,
You added the D.
yeah, T is 10, 222, plus 10 times 360 divided by 365, and that came out to be 229.
Okay.
Let's try and ballpark it. If August is what? That's about 2/3 of the way through the year, so 2/3 of the way from 0 to 360, that sounds like it's in about the right answer.
all right.
Yeah, it's basically, what fraction of a circle have we gone
But then
through?
where did you get, oh,
Oh, that.
the 0.65?
Ah, yes, so the cosine function magically will reduce this to a number between 0, or I should say between -1 and +1. That's its real power. It kind of reflects where it is in the cycle, and we multiplied it by this thing up front.
Okay, you multiply 229 by that.
Yeah.
Minus 23.5.
And it ends up with just over 15.
Oh, okay.
Yeah, 15 and a bit. Cool. And like I said, we glossed over it just because this is the kind of fun stuff that astronomers do when it's a cloudy night and they've got to get over. All right, last step. Let's get to where sunrise is. Ooh. And that's basically we're going to feed into this formula what we got from the last one. So we'll take that, what was it, positive 15 degrees, feed it into here. Oh, look, there's two
Oh
more
my God.
beautiful sines and cosines. And what's important here is that it depends on your latitude. So if you're doing this for anywhere here in northern Ohio, 41 is great. 41 and a half would be even better. But unless you go far north into, say, Winnipeg, or you go way down south to Miami, you're going to experience much the same conditions. So I like that. So anybody east or west of here is going to see the same solstice sunset conditions as we do. If you go east to Rome or west to Beijing, it'll be exactly the same. So it's kind of fun. If we moved our pavement all the way to Rome for some reason, it would still work. That's kind of, but if I move it, just down to Columbus, because that's to the south, our alignments will be off. It's fun. No, it's not, but I claim it's fun. All right, well, the end result of all this calculating is we come up with a number that on August 10th in Northeast Ohio, we should see the sun rise at 69.2 degrees, or let's round it to 69 degrees, because let's face it, my stone is not going to be a fraction of a degree wise when I go to mark this with a stone. Let's double check. Does this make sense? Okay, so we said on the summer solstice, it rises at, I put this on our forms. Pure northeast would be 45 degrees, but we rise at, 58 degrees in summer. And on the equinox dates in autumn, the sun will rise in due east. So here's where it is on the first day of summer. The sun rises here. It rises here the first day of autumn. August the 10th is in between that. So it should be somewhere in this area. We're just trying to estimate where it is. And what did we calculate again? Yeah, 69. Oh, look, that'll be right in between there. Okay, good. Phew. That's a great sanity check. Because if we had calculated something ridiculous like 231, we'd know we'd made a mistake. Because it should be, even if you just went to eyeball it, if you were moving a boulder around, if you wanted to mark where the sun would probably rise in August, it'd be somewhere in this wedge. But what I like is that it's closer to June than it is to September's sunrise, even though the date in August is a little bit closer to September. That's kind of fun. It's because it's not linear. It doesn't move the same amount from day to day. It speeds up as you get close to the middle. Yeah, it follows that great cosine or sine pattern. Oh, you guys are the best. Thanks. Oh, phew. Well, that was it. You are now your neighborhood experts on math and applying the solstice. I promise. We're done with the math part. It is kind of cool, though. I just like because it brings in some of our favorite math concepts and the real power of those functions. But it also...
The idea of it moving slowly, just more and more rapidly, that is intriguing.
I think that's really cool, yeah. And there's another side effect to this. It's when you're trying to track the time with sundials. Your sundial and your clock will disagree a little bit by a certain amount. That's called the equation of time. This is a standard graph that's on the back of sundials. And it'll tell you, well, you might be up to 12 or 15 minutes before or after what your sundial says. And what that is I love it. Oh, it's because the Earth doesn't go around the sun in a circle. This is one of the, if you ever wonder, why we, say, oh, the Earth goes around the sun in an oval. One of the ways people figured that out is because if we did, our sundials would always work. They wouldn't need this little correction factor. And we wouldn't see that speed up to the, around the equinoxes and where the sun is rising and setting. And we wouldn't see that cool figure 8 we saw in the sun pattern over the Kalanish standing stones. There's one other bit of fine print, which I'm amazed nobody brought up, because I set this up as like a bet. It feels like somebody always asks this when we talk about the winter solstice. is that if you look really carefully at the date, every day's sunrise and sunset times over the course of the month, they're always on page 2 of the newspaper with the weather data. And I read them, I'm sorry. You might notice the earliest sunrise, or so the earliest sunset and the latest sunrise don't coincide with the winter solstice. I mean, you'd think it would. It's the shortest day of the year, and yet the earliest sunrise actually happens about a week before, and the latest sunrise happens about a week before, and the earliest sunset happens about a week later.
Wow.
Ah.
Help me understand, you're gonna help us understand that, huh?
Absolutely, because this makes you your neighborhood's experts. So this is what's called a Sky Gazer's Almanac. It's in every good astronomy textbook. The magazine's always publish a new one for each year. And it's a weird way of thinking about the year, but it kind of goes from January 1st through the end of December. And it shows you just the nights. So this is the beginning of the night at 5 p.m. And over the course of the night on January 1st, all the way until the sun rises at 7 a.m., it tells you what you can expect. Here's when the planet Uranus is highest in the sky. Here's when Venus rises. Here's when, the star Sirius appears and disappears. It's kind of great. So if you want to know, oh, we're going stargazing on September 20th, what planets will we be able to see? Oh, cool, Jupiter by midnight? That should be a great sight. But I love it because it also shows you how long the nights are in the winter and how short the nights are in the summer, because it makes this hourglass shape. Like there's this skinny waist here where the nights aren't very long in the summertime. The other thing is if you stand back from it, it's not symmetrical. It doesn't look exactly the same from right to left. If the Earth went around the sun in a circle, this would be. It would look the same left to right.
Yeah.
So all I did was, because this one talks about nighttime, because that's what astronomers care about, I just flipped it over to talk about daytime. So here we are, from January 1st to winter again. Nice. Well, actually, sorry, I went from March to March. Here's how long a daylight session we get, and then we get some darkness on either side of midnight. So our days are long here in June, and they're short here in December, and they go back a little bit. But you're right, there's a little bit of a lag in when we get our latest sunrise and our earliest sunset. And the winter solstice here is in the red. So just a few days on either side.
Wow.
And it's kind of cool. If they all coincided, we would know that our planet goes around the sun in a perfect circle. But because it's an oval, and we're a little bit tilted, sometimes we catch the sun a little bit earlier coming around that planet. And sometimes we go into the sun a little bit later coming around it on the other side. It's kind of fun. But not as much fun as actually doing it. So, oh, nice. I'm going to hide this. Because, do you guys like plays?
Yeah.
Good, you're sure about to be in one. Oh, nice.
Oh my God.
I brought my favorite way. This is my most intuitive way of grasping the whole solstice concept, is to act it out for ourselves. Sorry, I'm going to pick on you. What's your name?
Bill.
Not anymore, you're the sun. Sorry.
Somehow I like this.
So if you ever come to our winter solstice programs at the West Woods, I wear a giant sun costume that is 4 feet across. And I kind of look like the Monsters, Inc. character. But if we made the sun that size, about 4 feet across, that's my hat from that costume. It makes my favorite planet about this big. The Earth here is this little marble that's maybe a quarter of an inch across. Oh, nice! So I want you as folks to guess, if the sun were about the size of a large beach ball, about 4 feet across, the Earth were this big, ballpark, how far apart would you guess they'd be? And it's okay to be totally wrong. We're taking random guesses.
6 feet.
Oh, good guess. No, it works out. It's actually like 238 feet. So we couldn't even fit it in the library, which is why I didn't lay it out. I did walk it out. That'll take you way down to the speed bumps on the driveway coming in from here in this room.
Wow.
So this is the other question people usually ask about the solstice is, aren't the seasons caused by the sun being closer to or farther than the sun? Or I should say the Earth being closer to or farther than the sun? But what I like is, so if you imagine, we had a 4 foot wide sun here in this room, and we put this thing out by the speed bumps. That's its average distance. Oh, nice. And here I can show you, without here in the room, the farthest distance between the Earth and the sun, it would be that much farther away. about this much.
Really?
So I know, over the course of, what, 230 feet from here to the sun, the Earth moves closer by about that much,
Huh.
which is less than a third of the width of the sun. So I know, people say, oh no, the seasons happen because you're closer or farther. It has no effect on our seasons. Our seasons all have to do with something else. The magic word is,
The tilt.
oh, you guys are awesome, the tilt. What's your name?
Jane.
Not anymore, you get to be the Earth, Jane.
Yay!
Oh. And I have my favorite doing, I'm sorry, you have to get up and do some orbiting. Are you cool with that? Wonderful. Oh, there you're standing up and showing what you got. Oh, wow, she even knew what to do. Oh, it's an Earth on a stick, and it rotates. Ooh, so wow, like a week has gone by. Nice.
Wow.
So yeah, that's how it rotates day by day. And you'll also have another cycle of orbiting around the mighty sun here. So, I mean, if we really wanted to be fancy, we'd make you stand 230 feet away out in the
No.
cold. But that's no fun. We're just going to systematically do it here in the room.
Okay.
Do you mind doing a quick orbit around these chairs and coming right back?
Oh, no.
Go for it. All right, you've got to rotate while you do it. Oh, I know this is like chewing gum and walking. Nice. So that'll be a year from, let's say this was, I don't know, what's today? December the 4th, 5th, 6th. All the way back. Oh, so happy birthday, everybody. We're about to get 1 year older.
You need me to send you a solar flare?
That would warm things up a little bit. Oh, that was nice. Great. Give her a cool hand. And look at the sun as well. All right, you have one other person who's willing to be the Earth in this. All right. You gonna try? No? All right. Well, sorry. You get to do it again. All right, go for it. Because we didn't do a very good model. We have to add one more factor to make this more realistic.
We got to tilt the Earth.
We gotta tilt the Earth.
I don't know.
So yeah, if our plane that we orbit the sun in is like the floor that we're walking on, we've got that. Hold on, steady. We need one more outer space thing. Good guess.
Star.
Polaris, the North Star. Ooh, I'm gonna pick on Amy for this. Do you mind?
That's fine.
You get the easiest job. You just kind of hold that in a Statue of Liberty pose
Okay.
and stand right over here. So whatever, I think that's north in real life. But this will be pretend north towards her. Okay, you ready, Earth? You got a real challenge. Not only do you have to orbit around the chairs, but here's the real challenge. You've got to keep this stick, your axle, pointed exactly at that North Star. I know, in the real world, that's about 23 degrees away from vertical, but here, we can't make Amy infinitely tall, so. Oh, nice. She's doing it well done, keeping that tilt. Pointed right at Amy. So if you watch as the Earth goes around, for half the year, the north half of the planet is tipped towards the sun. Half of the year, the north half of the planet is tipped away from the sun. Like right now, imagine the Earth is a delicious rotisserie chicken. Because, and I'm hungry enough, that sounds pretty good. But if I pause you here, this is pretty close to our winter solstice. Oh, wait, we're still rotating, we're rotating. No matter how much we lathe ourselves around, the north part of the Earth is in the shadow for a lot of times because we're tipped away from that sun over there. Because of a cool concept called the conservation of angular momentum, the Earth will always keep its axis pointed in that direction. It just happens to be pointed towards this particular star called Polaris. It could have been somewhere else. In fact, at certain distant times in the past, it has. Oh, she's still got this. Well done! Oh, an air high five. Well done. Thank you guys, and thanks, son. Oh, nice. And thanks, Amy the North Star. See? Everybody's just following you. Oh, good stuff. So, like I said, because... Oh, go ahead.
What did you call that? The pitch of the Earth,
Oh, yeah.
you go, and it's 23 and a half or whatever you said.
Sure. So that's...
But to Polaris, to the North Star, there was a, would you call it a phenomena or
Oh, sure.
a rule? What was that?
That's a good question. Usually the term for it is our axial tilt. So our best guess is that most planets going around the sun would more or less... Oh, I should get my actual Earth here. Everything in the solar system orbits around the sun the same direction. Well, except for a few tiny things that don't. We think they might be visitors from outside. But all the big planets orbit around the sun in the same pattern. The sun itself rotates in the same way. Here's my favorite way to remember it. Go ahead and give a thumbs up with your right hand. All right, imagine you're holding the whole world in your hand. If north is up, where your thumb is pointed, the Earth rotates the way your fingers wrap around your hand. I know. That's also the way every single planet in our solar system orbits around the sun. If north is up, we go right-handed. We live in a right-handed solar system.
Huh.
So all the planets go around that way. There's a few asteroids who go the other way, but they're kind of weirdos. We think they might be visitors from somewhere else. But we figure most planets are pretty close to straight up and down with their rotational axis at a right angle to the plane of the solar system. A few are tilted here and there. Our planet seems to be tilted about 23 degrees away from vertical. That's our axial tilt. And the winner for the big planets is the planet Uranus, which is tilted at about 89 degrees.
Whoa.
So I know, it really feels like we think it used to stand upright and then something knocked it over. And then there's the oddball. The planet Venus is the only kind of upside down compared to the others planet. If you will, that's the only left-handed planet. It rotates this way. It still orbits the sun right-handedly, the same as the others, but it's got to be different. We figure it's a right-handed planet that got knocked upside down. At least that's the best guess. Nobody was around to see it. Oh, go ahead.
I've got a quick question.
I'm pointing with the Earth. This feels very
Yeah,
authoritative.
I don't know how long the answer would be, but
Sure.
when you get the moon, full moon or whatever.
Oh, sure.
Now, is the moon spinning as it, you know,
Oh, nice.
you know what I mean? Is it going
Yeah.
around, or is it just, but I know it's spinning, but it doesn't make any sense to me.
Oh, I know. It is very weird and very odd because we spend our whole life stuck on the Earth. The real question is, why don't we see the Earth or see the moon rotate? And so the short answer is, yeah, it rotates, but it always keeps the same side facing the Earth. So it feels like it doesn't rotate. It looks like it doesn't rotate because we're always seeing the same side with that, man in the moon markings on it. But here's my favorite way to think. If it didn't rotate, if it did what her axis did and it always pointed at, let's say, the North Star, then we would see the backside of the moon every once in a while. In order for it to always keep one side facing at the Earth, it has to turn like a dance partner to keep that side towards the Earth.
Okay.
I know, yeah, and I'll put in a plug. We just did our cool All About the Moon program. I guess we might have to do that one again, because it's tons of fun. We actually, my favorite way to do this is we have somebody as the Earth standing still. The other person on the moon has a laser pointer, and you have to keep your laser pointer hitting the person who's the Earth. It's a lot of fun, and nobody gets hurt. But if you don't rotate your body, you'll never keep your laser pointer hitting the Earth.
Plus, wouldn't it then defy Einstein's theory of relativity?
It would defy a
Because it
whole
wasn't
lot of our...
moving rolling through space there.
Right, it would defy a whole lot of our understandings of how nature works. If the Earth, the moon didn't rotate. Good question. That's one of those weird counterfactuals. If the moon ever stops
It just
rotating.
happens to be rotating at just the right rate.
Yeah.
The same
Thank you for
phase
this.
towards the-
Yeah, it's called tidal locking, and that seems to be really common. Like, if we lived on Jupiter, where there are more than 60 moons, almost all of them are tidally locked to face Jupiter's surface. So if you live on Jupiter, you'll always see the same side of those moons. It's just, we don't see that as well because we live here on the Earth. But I mean, when we look at Jupiter's moons, because we're not on Jupiter, we see those moons rotate. We'll see their back sides, we'll see their front sides. But if you were stuck on Jupiter, you'd only see the one side. It's kind of cool.
Yeah.
Okay.
All right, so one last thing I want to show.
Can I ask one more question?
No, I'm just kidding, go ahead.
Why is that?
Why is what?
Why is it that all these moons rotate at just
Oh.
the right?
You just-
Tidal locking? Yeah, the short answer seems to be gravity. The long answer is, you'll have to come to our moon program and talk about it more in detail.
Yeah.
The short answer is, it seems like if they don't synchronize exactly, then let's say you build a new moon around the Earth and you had it rotating at a different speed, eventually it's going to feel a drag if it's spinning a little faster. Parts of it that are pulling away, well, Earth's gravity will always be dragging it back in this direction, and that'll slow down its speed until eventually they synchronize, and it keeps,
So,
again, like a do-si-do dance
it's
partner.
like over time it's creating an equilibrium.
Yeah.
Okay.
So like I said, even if you did spin up a cool new moon, over many, many, many years, the Earth's gravity will slowly slow it down until it matches that magic synchronization speed. Cool stuff. Okay. So one of the reasons we have this program here in this room is because it's big enough to accommodate our huge inflatable planetarium. And we had hoped that we'd all get to coincide and see that, and we could show you some of these cycles in the sky that I'm talking about. But then we'd all be trapped in a big balloon breathing the same air, and it's not the healthiest choice. So instead, I'm going to try and shine it up here on the screen. Amy, do you want to try and dim some of the lights? Let's see if we can make this easier to see. Is that okay? It's not too dark?
No.
Nice. So that circle, if you can imagine, you're lying on your back, looking up, and that's the entire sky. So this is what would fill up our whole dome ceiling in a planetarium. So south is down here, north is over there. Okay, I wanted to show you what a year looks like in fast forward if you live on planet Earth. So hang on a moment. Oh, good question. Why are east and west flipped?
Yeah.
Oh, great question. You guys are getting to all the good ones. I love it. Okay, and the short answer is, when you look at a map, oh, Amy, do you mind putting the lights back on? Thanks. When you look at a map of the Earth, it's like you could stand on it. North is, oh, this is a real one. North is that way, east is that way, south and west. We're looking at a map of the sky. So if you flip it up, two of the directions are flipped.
Oh.
Yeah, so like in real life, that's still east, and that's still west, but when you take a map of the sky and hang it on the wall, it looks flipped.
Oh.
I know, that's just because we couldn't take this thing and nail it to the ceiling. If we nailed it to the ceiling, it would be perfect, but you're right.
Okay.
Okay, cool. Do you mind, Miss Amy? Okay. Let's try a year. Ooh. In fast forward. Right? Oh, it's good stuff. So if we jump ahead a few days, ooh. What I've done is I've summarized what a year's worth of sunrises and sunsets would look like. So this is south, north, west, and east. The sun will rise over here on our winter solstice, kind of in between east and south, in the southeast. Gets to here in midday, sets over there. That's all the sunlight we get in winter. Barely 9 hours of it. Whereas in the summer, it rises way over here in the northeast, gets very high, almost straight overhead, but not quite, and then sets way over there. And we get the reverse, we only get like 9 hours of darkness. That's kind of fun.
Yes.
And every day in between, after the December solstice, day after day after day after day after day, oh yeah, things will, oh yeah. I put a protractor on here so you can measure the angles. The highest the sun ever gets here in Northeast Ohio is 74 degrees, so if they ever ask that at trivia night, you'll be able to say, oh, it's 74 degrees. The only places on Earth where the sun gets to 90 degrees straight overhead, that's the tropics, the region around the equator. And since you're experts, you know the latitude of the tropics. It's 23.5 degrees north or south of the equator. Ah, that nifty tilt number again. Oh, good stuff. Okay, so if we speed up time a little bit more, day after day after day after day, after the winter solstice, what's going on?
Get more sun.
Yeah, we get more sun. It looks like the sun's getting higher in the sky or farther towards the north. Until we get to the next solstice in June, when the sun pulls another U-turn, and creeps back down until next December. Oh, so happy birthday. You just got a year older. So yeah, if I were in charge of the names, we wouldn't call them the solstices. We would call them the sun U-turn days, where the sun stops getting lower and or stops getting higher and it goes around.
Wow.
I know. So if we really speed this up, this is a little harder to do outside because time doesn't like to speed up. From June to December and back to June again. The sun keeps wiggling, oscillating in that nifty figure 8 pattern. High in June, low in December. I also like this because it makes it feel like we live inside a volleyball. Yeah, that kind of summarizes a whole year's worth of sunrises and sunsets really well. So like I said, if you were an ancient Ohioan and you wanted to mark where those sunrises were, you would just need to mark a few points on your horizon, and you're all set with a calendar. Good stuff. Ooh. Okay, one last one. So that's the view trapped here on planet Earth and in Montville, no less. So all right, let's take a broader view and see what it looks like from outer space. Ooh, this always makes me a little bit dizzy.
Yeah.
So if you can get outside, we were on one of those space probes way at the outer edge of our solar system. So the green line is the Earth's equator stretched out into the sky. And the red line is the position we see the sun appear to follow. And these squares are kind of showing you where it is at our seasonal crossings. So our equinox dates are where the equator and the sun's path match. And in the winter, the sun is farther south of it, and in the summer, it's farther north. Cool stuff. All right, so let's zoom in here on my favorite part of the solar system. There's the sun, and you might notice a few things buzzing around it.
The sun rotates too, right?
Absolutely.
Well,
Same direction right-handedly as the planets, only it takes it about 3 weeks to rotate. That's weird, because it's not a solid object, so parts of it rotate faster. It's a little gooey. Oh, look, my favorite planet.
You said, you referred to the way your fingers point,
Mhm.
but you don't refer to it as counterclock?
Oh, you could. It's clockwise and counterclockwise are great words for two-dimensional things like clocks that you can only look at from one side.
Not.
Yeah, in a three-dimensional thing, it gets kind of confusing. Because if you're in Australia, that same motion that I'm calling right-handed looks clockwise rather than counterclockwise. So the least confusing thing is to just say right-handedly.
Yeah, gotcha.
So yeah, the way I like to say it is we move planet-wise. Good stuff. So in the summertime, we're kind of bathed in more sunlight, flipping around half a year. And the northern hemisphere is the side that isn't getting as much sunlight. We spend a lot more time in the shadow. Good stuff. I know. Fun stuff. Okay, one last one, I promise. This will be real fast. I'll save you a trip to the planetarium. What if that was kind of hovering out in space and just seeing how our tilt affects how the sunlight hits us over the course of a year? What if you were actually like hovering above the Earth's equator and you could watch a whole year go by? So for me, this helps really explain what effect that tilt has on how much sunlight we get. All right. So there's our Earth, and we've stretched the latitude and longitude grid out into the sky, but I'm just going to keep the equator, and we'll zoom in a little bit. Hey, look, there's North America, cool. So we'll keep that equator there in the background. Oh, yeah. And if we watch time go by, see how the sunlight is shifting? So here's December, there, when we're a little bit tipped. And then June, we get more sunlight. The folks way down in the south are getting the reverse. All right, wait, let's take a little trip. We're going to go farther west so we can see this better. Hang on a moment. Let's go to the middle of the Pacific. Ooh. From down here, I should say above Antarctica. Ooh. All right, over the course of a year, in June, in December, and in June. So yeah, that really affects our seasons, and they're also kind of flipped. So that, you know, they get more sunshine in our winter down south, and we get the reverse. All right, one last one. Let's come to right where we can watch our planet going from day to night. All right. Fun stuff, right? You didn't know we'd be doing this much world traveling.
Yeah.
All right, so above our equator, but look, oh look, there's Hawaii. That little string of lights in the middle of the Pacific Ocean. There's the west coast of North America. Here comes Australia and Japan. Okay, let's make a year go by from this winter time when the north half isn't getting as much sunlight. It's getting a lot more shadow. In the summer, when our part of the planet is tilted to get a whole lot more sunshine. back to winter,
Wow.
back to summer, and it never stops, year in, year out, like clockwork. That's kind of fun. It really helps get you, a little bit of perspective. I mean, the cool thing is that humans have puzzled this out, even though we've never gotten that perspective from an outside spaceship until very recently. But the folks were able to puzzle this out just by watching where the sun rose and set on the horizon. Okay, I think we're ready for our lights. Well, thanks. You guys have been amazing. Pat yourselves in the back. That was a whole lot of recreational science and math to go through on a blustery Monday. If you got any other questions, we're happy to do our best to answer them. Or you can check out Amy's amazing collection of books back there. Nice son.
That was great.
Or if you have like a topic, hey, could we do a Skywatchers presentation? I know we need to do one about the moon again. That would be awesome. No worries. We can always do it again. Well, thanks.
Thank you.
Thank
You guys
you.
are the best.